Hey, science explorers, Will here. Are you ready for some seriously cool science that you can do right in your own home? That's right. We're about to dive into a world of amazing discoveries using everyday items. Forget fancy laboratories and complicated equipment. For a moment, today, we're going to prove that science isn't just in textbooks. It's all around us, fizzing, floating, and even disappearing. So, grab your curiosity hats, because things are about to get wonderfully experimental. Get ready to be amazed, because today, we're going to turn your kitchen into a science lab with these super fun and safe experiments. We'll be mixing, pouring, and observing some incredible phenomena. Each experiment is designed to be easy to follow, super engaging, and most importantly, will teach us a little something about the way our amazing world works. From chemical reactions that go whoosh to understanding why some things float and others don't. It's going to be an adventure. So, are you with me? Awesome. We're going to explore density, chemical reactions, and even the magic of polymers. These aren't just tricks. They're real science principles in action. By the end of this, you'll not only have had a blast, but you'll also see your kitchen in a whole new light, as a place where incredible scientific discoveries can happen any day of the week. Let's get started on our scientific journey. Alright, first up, we're tackling a true classic, a legend in the world of home science, the baking soda and vinegar volcano. This experiment is an absolute blast, and I mean that literally, well, almost. We're going to witness a chemical reaction unfold right before our very eyes, creating a miniature eruption that's both exciting and incredibly informative. What we're doing here is combining two common household ingredients to produce something entirely new. And that, my friends, is the heart of chemistry. So, what do you need for this volcanic adventure? It's super simple. Grab some baking soda, that's sodium bicarbonate for you science whizzes, and some regular white vinegar, which is mostly acetic acid and water. You'll also want a small bottle or jar to act as your volcano's chamber, and perhaps a tray or plate underneath to catch any, shall we say, lava overflow. Safety first, even with kitchen-safe ingredients, means keeping messes contained. A little bit of dish soap can make the eruption even foamier, and a few drops of red food coloring. Chef's kiss for that authentic lava look. Now, let's build our volcano. Place your bottle or jar on the tray. This is where the magic, or rather, the science, will happen. Carefully spoon a few tablespoons of baking soda into the bottle. Think of this as loading up the magma chamber of a real volcano. The more baking soda you add, potentially the bigger the reaction. But let's start with a moderate amount. We're observing a principle here. The amount of reactants can influence the scale of the reaction. It's all about cause and effect, a fundamental concept in science. Next, if you're going for visual flair, add a squirt of dish soap and a few drops of red food coloring into the bottle with the baking soda. The dish soap will help trap the gas we're about to create, making for more impressive, longer-lasting bubbles and foam. The food coloring, well, that just makes it look awesome, doesn't it? Science can be beautiful too. Remember, observation is key in any experiment, so pay attention to what happens at each step. The moment of truth is approaching. Take your vinegar. This is our acidic component, ready to react with the alkaline baking soda. When these two meet, they're not just going to sit there politely. They're going to get busy. This is an acid-base reaction, a fundamental chemical process that happens all around us, even inside us. Are you ready? Take a deep breath, because here comes the eruption. This anticipation is part of the fun of science. And what will happen? Moment. Slowly, or quickly for a more dramatic effect, pour the vinegar into the bottle containing the baking soda mixture. And kaboom. Well, a mini, foamy, kitchen-safe kaboom. You'll see an immediate fizzing, bubbling, and an eruption of foam that hopefully, if you added food coloring, looks like lava flowing down the sides of your volcano. What you're witnessing is the rapid production of carbon dioxide gas. It's this gas that creates all those bubbles and the pressure for the eruption. But what's really going on here? When the acetic acid in the vinegar reacts with the sodium bicarbonate baking soda, they undergo a chemical transformation. The products of this reaction are water, a type of salt called sodium acetate, and lots of carbon dioxide gas, CO2. This CO2 gas is invisible, but it needs space, and as it forms rapidly, it pushes its way out, carrying the liquid and soap with it, creating our fantastic foamy eruption. It's not magic, it's chemistry in action. Consider this: real volcanoes also release gases, though much hotter and more dangerous ones. Our kitchen volcano is a fantastic, safe way to understand the basic principle of gas production and pressure causing an eruption. You can experiment with different amounts of baking soda and vinegar to see how it changes the reaction. Does more vinegar mean a bigger eruption? What about more baking soda? That's the scientific method. Ask a question, form a hypothesis, test it, and observe. Next up, we're going to investigate something that seems a bit like magic, but I assure you, it's pure science. We call this the floating egg experiment. Have you ever wondered why some things float in water and others sink like a stone? It all comes down to a super important scientific concept called density. And today, we're going to see density in action using just an egg, some water, and a common kitchen ingredient, salt. This is going to be egg-cellent. So, for this experiment, you'll need a raw egg. Be gentle with it. A tall, clear glass or jar, water, and of course, table salt. The clear glass is important, so we can observe exactly what's happening. Science is all about observation, after all. We're going to compare what happens to the egg in plain tap water versus what happens when we change the water just a little bit. It's a simple setup, but it demonstrates a powerful principle that governs why massive steel ships can float. Let's start by filling our clear glass about halfway with plain tap water. Now, very gently, lower the raw egg into the water. What do you observe? Chances are the egg sinks straight to the bottom. Plop. This happens because the egg is denser than the plain tap water. Denser simply means that for the same amount of space or volume, the egg has more stuff, mass, packed into it than the water does. So, down it goes, unable to be supported by the less dense water. Now, let's see if we can change that. Carefully remove the egg from the glass. Set it aside safely. Now, to the water in the glass, we're going to start adding salt. Add a good amount. Say a couple of tablespoons to start, and stir it thoroughly until the salt dissolves. And you might need to stir for a minute or two. Keep adding salt and stirring until no more salt will dissolve, or until you've added quite a bit, maybe 5 or 6 tablespoons for a standard glass. We are fundamentally changing the water. What we're doing by dissolving salt in the water is increasing the water's density. The salt particles are now occupying the spaces between the water molecules, adding more mass to the same volume of water. This salty water is now heavier or denser than the plain tap water we started with. It's like packing more people into the same size car. The car gets heavier, right? The water is getting heavier in a sense, without its volume changing much. Now for the exciting part. Take that same egg that sank before and gently lower it into your salty water solution. What happens this time? With enough salt dissolved, you should see the egg magically float. It might float right at the surface, or it might hover in the middle of the water. How cool is that? The egg itself hasn't changed its density, but we've made the water denser than the egg. When the liquid is denser than the object placed in it, the object floats. This is all thanks to buoyancy, which is the upward force exerted by a fluid that opposes the weight of an immersed object. Archimedes, a brilliant, ancient Greek scientist, figured this out. When the buoyant force, the upward push from the water, is greater than the weight of the egg floats. By making the water denser with salt, we increased its ability to provide that upward buoyant force. It's a delicate balance of forces. You can even try to create a situation where the egg hovers in the middle. If your egg is floating very high, you can try carefully adding a little bit of fresh water on top. Pour it slowly down the side of the glass to avoid mixing too quickly. You might be able to get the egg to suspend itself between a layer of salty water at the bottom and less salty water at the top. This shows how density can vary even within the same container of liquid. Think about the ocean. It's salty, which helps big ships and you float more easily than in a freshwater lake. Are you ready to create something truly beautiful and scientific at the same time? Our next experiment is called Rainbow in a Glass, and it's all about, you guessed it, density again. But this time, instead of just making an egg float, we're going to stack different liquids on top of each other to create a colorful tower. It's a visual feast that perfectly demonstrates how liquids of different densities behave when they're in the same container. It's like a liquid layer cake. For this vibrant experiment, you'll need a tall, clear glass or a narrow jar. The narrower it is, the more distinct your layers will often appear. Then gather your liquids. Good candidates include honey, corn syrup, especially if you can get a dark and a light version or color one. Dish soap, try to get a colorful one. Plain water, which you can color with food coloring, and vegetable oil or rubbing alcohol, which you can also color. The key is to have liquids with noticeably different densities. The secret to a successful density tower is twofold: choosing liquids with different weights for their volume and pouring them very, very carefully. We want the densest, heaviest liquid at the bottom and the least dense, lightest liquid at the top. Think about it. If you put a heavy rock on a pillow, the rock sinks. If you put a feather on a pillow, it sits on top. Liquids behave similarly based on their density. So we need to figure out our order. Generally, honey and corn syrup are very dense, followed by dish soap, then water, and finally oil or rubbing alcohol are usually the least dense. Let's start building our rainbow. Begin with your densest liquid, and let's say it's honey. Pour a layer of honey into the bottom of your glass. Try to make it about an inch thick, or however much looks good to you. Now, for the next layer, let's say it's dish soap. This is where the careful pouring technique comes in. You don't want to just dump it in, as that will cause the liquids to mix. Instead, tilt the glass slightly and pour the dish soap very slowly down the inside wall of the glass. Let it gently flow onto the surface of the honey. If you're using water next, you might want to color it first with a few drops of food coloring. Choose a color that will contrast nicely with the dish soap and the layer that will go on top of it. Again, tilt the glass and pour the colored water extremely slowly down the side onto the surface of the dish soap. You should start to see distinct layers forming. It's like magic, but it's science. Each liquid is finding its place based on its density, with the heavier ones settling below the lighter ones. Continue this process with your other liquids. Perhaps vegetable oil is next. Pour it slowly down the side. Then, if you have rubbing alcohol, which is often less dense than oil, you can color it a different shade and carefully add it as your top layer. Remember, patience and a steady hand are your best friends here. The slower you pour, the cleaner your layers will be. It's a fantastic exercise in careful measurement and observation. Once you've added all your layers, stand back and admire your creation. You should have a beautiful column of distinct, colorful liquids, a veritable rainbow in a glass. This works because the liquids are immiscible, or mostly immiscible, meaning they don't mix easily, and have different densities. The honey is at the bottom because it packs more mass into a given volume than, say, the oil at the top. Each layer is literally floating on the denser layer beneath it. You can even take this experiment further. What happens if you gently drop small objects into your density tower? Try a small plastic bead, a grape, or a tiny piece of metal like a paperclip with adult supervision if needed. Where do they settle? An object will sink until it reaches a liquid layer that is denser than itself. This demonstrates how submarines can adjust their depth by changing their overall density. Science is truly all around us in the most colorful ways. Shh. Want to know a secret? Or better yet, want to send one? Our next experiment delves into the clandestine world of invisible ink. We're going to write messages that no one can see, and then, like master spies, reveal them using a little bit of scientific know-how. This is a classic experiment that combines a bit of mystery with some fascinating chemistry. It's all about making something appear as if by magic, but as always, there's a perfectly good scientific explanation behind it. What do you need for this top secret mission? Your primary invisible ink ingredient is something you probably have in your fridge: lemon juice. That's right, the sour power of lemons holds the key. You'll also need a cotton swab or a small paintbrush to act as your writing tool, a piece of white paper, and a heat source to reveal the message. For the heat source, an adult's help is absolutely essential. This could be a lamp bulb, an incandescent one that gets warm, or gentle heat from an iron, again with adult supervision and on a low setting, protecting the surface underneath. Safety first. Always. Let's prepare our invisible ink. Squeeze some fresh lemon juice into a small bowl or dish. You don't need a lot, just enough to dip your cotton swab or paintbrush into. Lemon juice is a mild acid, and it contains carbon compounds. These carbon compounds are the secret to our invisible ink. When you write with it, you're applying these compounds to the paper, but they're mostly colorless when they dry, making your message, well, invisible. Now, dip your cotton swab or paintbrush into the lemon juice, getting just a little bit on the tip. Don't soak it too much, or your paper might get too wet and crinkly. Write your secret message or draw a clandestine picture on your white paper. Try not to press too hard. As the lemon juice dries, your message will seemingly disappear. It's still there, of course, just hidden from plain sight. Let the paper dry completely before you attempt to reveal it. Patience, young spy. Patience. Once your message is completely dry and invisible, it's time for the grand reveal. This is where adult help is crucial. If you're using a lamp, hold the paper carefully near a warm, not hot, incandescent bulb. Don't let the paper touch the bulb. If an adult is using an iron, they should set it to a low heat setting, no steam, and gently pass it over the paper, perhaps with another piece of paper on top for protection. The key is gentle, even heat. What you should start to see is your secret message slowly appearing on the paper, turning a light brown or brownish color. How amazing is that? Your invisible writing is now visible. But what's the science behind this seemingly magical transformation? It's not magic. It's a chemical process called oxidation. And the carbon compounds in the lemon juice are the stars of the show. When you heat the paper with the dried lemon juice on it, the lemon juice residue heats up faster than the paper itself. The compounds in the lemon juice begin to break down or oxidize. This process releases carbon. When carbon is heated in this way, it can char or caramelize, turning brown. So the parts of the paper where you wrote with lemon juice turn brown, while the rest of the paper remains white, revealing your message. This is a simplified version of what happens when you toast bread or marshmallows. The heat causes chemical changes that result in browning. Other mild acids, like milk or even onion juice, can also work as invisible inks using a similar principle. So you've not only learned how to send secret messages, but you've also explored a bit of organic chemistry and the effects of heat on different substances. Pretty cool for a simple lemon, wouldn't you agree? Go ahead, share some secrets safely. Get ready to get your hands a little messy, because for our final experiment, we're making homemade slime. That's right, that gooey, stretchy, fascinating substance that kids, and let's be honest, adults too, love to play with. But slime isn't just fun. It's also a fantastic way to learn about some really cool science, specifically about something called polymers. We're going to mix a few simple ingredients and watch them transform into something entirely new and wonderfully weird. So what do you need to concoct your very own batch of slime? The basic recipe usually involves white school glue, the kind that contains PVA or polyvinyl acetate, baking soda, and contact lens solution, specifically a contact lens solution that contains boric acid and sodium borate. These are our key slime activating ingredients. You might also want some food coloring to make your slime vibrant, or glitter if you're feeling fancy. And of course a bowl for mixing and something to stir with. Let's start by pouring some of your white school glue into the mixing bowl. The amount of glue you use will determine how much slime you make. About half a cup is a good starting point. If you want colored slime, now is the time to add a few drops of your chosen food coloring and stir it into the glue until it's evenly mixed. This is your base, and the glue itself is made of long chain-like molecules called polymers. Think of them as long strands of spaghetti. Next, add about half a teaspoon of baking soda to your glue mixture and stir it in thoroughly. The baking soda helps to firm up the slime and also plays a role in the chemical reaction that's about to happen. It helps control the texture. Make sure it's well combined with the glue. At this point, your mixture will still be pretty sticky and glue-like, but we're about to change that significantly with our magic ingredient. Now, for the activator, the contact lens solution. This is where the real transformation begins. Slowly start adding the contact lens solution to your glue and baking soda mixture, a little bit at a time, while stirring continuously. You'll notice the mixture starting to pull away from the sides of the bowl and thicken up. It will begin to form a blob. Keep adding small amounts of contact lens, solution, and stirring, or kneading with your hands once it gets thick enough, until the slime reaches your desired consistency. What's happening here is a fascinating bit of chemistry. The polyvinyl acetate, PVA, in the glue consists of long, separate polymer chains. The boric acid and sodium borate in the contact lens solution act as cross-linking agents. Imagine these cross-linkers as tiny bridges that connect those long, spaghetti-like polymer strands together. When these strands get linked, they can no longer slide past each other as easily. This is what changes the liquid glue into a semi-solid, stretchy, gooey substance we call slime. The more contact lens solution you add, to a point, the firmer your slime will become. If your slime is too sticky, try adding a tiny bit more contact lens solution. If it's too stiff, you might have added too much. It's all about finding that perfect balance. Once it's no longer super sticky, you can take it out of the bowl and knead it with your hands. Now, stretching it, squishing it, and observing its properties is all part of the fun and the science. This slime is a type of non-Newtonian fluid, which means its viscosity, or how easily it flows, changes depending on the stress applied to it. If you pull it slowly, it stretches. If you try to snap it quickly, it might break. Some slimes can even bounce. You've just created a polymer network, and by playing with it, you're exploring material science. How cool is that? You've taken simple liquids and, through chemistry, created something with entirely new and fascinating properties. Wow, what an incredible journey through the world of kitchen science we've had today. From the explosive fun of our baking soda volcano, to the mysterious floating egg, the beautiful density rainbow, our top secret invisible ink, and finally, the gooey greatness of homemade slime. We've seen chemistry and physics come alive right before our eyes, using things we can find all around us. I hope you've seen just how exciting and accessible science can be. Remember, science isn't just about knowing facts, it's about curiosity, observation, and experimentation. It's about asking why and what if, and then trying to find the answers. Each of these experiments demonstrated a fundamental scientific principle, from chemical reactions and density to oxidation, and the amazing properties of polymers. And the best part, you were the scientist making it all happen. That's the true power of hands-on learning. So now it's your turn to continue the exploration. Try these experiments and share your results in the comments. Did your volcano erupt spectacularly? Did your egg float? What colors did you use for your density tower? I'd love to hear all about your scientific adventures. Keep asking questions. Keep experimenting. Safely, of course. And never stop being curious about the amazing world around you. Until next time, keep thinking like a scientist.